The second example, as I told you, is calculating streamlines, path lines and streak lines. In the last example we have not discussed streak lines. In this example we will also discuss streak lines. Other objective is to see how to find out these lines and plot them for an unsteady flow, and we have already discussed for unsteady flow these lines are not same. So, you will also see that these lines are not same, they do not coincide, and then you will also see how to plot a streak line. Those are the special features of this example. Other things are a little bit common with the previous example. Okay. We start with this velocity field. The velocity field is given by, once again it has both x component and y component. The x component depends on x and also time, that is where time is brought into the whole problem, and y component is just a function of y. Because time, the x component is a function of time, it is a unsteady flow field. Okay. If it were not there, it is just a steady flow field like in the previous case. Now, this example also illustrate, we have been talking about streamline at a particular instant, that will also be emphasized here. Now, streamline, as we have seen, represents the flow at a particular time instant. Okay. Now, let us start with the equation for the streamline, which I used in the previous example. Dy by dx is equal to v by vx, and do a rearrangement convenient for integration as dy by vy, and vy is equal to y. Right hand side we have dx by vx. Now, vx is x by 1 plus t. Now, you will have to integrate the left hand side, integrate the right hand side. When you integrate, remember, because streamlines at a particular instant, t is just a constant given value to you. I want streamline at first second, 0 second. So, you integrate as usual with respect to y, as usual with respect to x, keeping just t as a constant. So, left hand side is ln y, right hand side 1 plus t is just a constant, okay, and then dx by x on integration gives you ln x, the constant is ln c, which we can rearrange and express the equation for streamline as y equal to c x power 1 plus t, 1 plus t. Please pay attention that you have a time here. So, this equation y equal to c x plus 1 x power 1 plus t is for a particular time t. Based on the time t, for example, which we will see now, okay, we can plot a family of streamlines at time t by varying parameter c. In the previous example there was no time, you just varied c and got a family of streamlines. In this case, at every instant time of t, you will get a family of streamlines, we will see that now. Okay, let us take t equal to 0. When you substitute t equal to 0, you get y equal to cx, which is linear. So, these are the family of streamlines. What is it I have done? I have taken different values of c here and then plotted this equation, that is all I have done here. The x axis, y axis, taken c equal to 1, 2, 3 etc. here, and then plotted this linear relationship y equal to x, y equal to x, y equal to 3x. All these are straight lines. Now, let us say some other instant I take as t equal to 0.5. Now, what happens? It becomes c y equal to c x power 1.5 becomes non-linear. Just want to say that the streamlines differ, and now I get another family of streamlines by once again varying the value of c, y equal to x power 1.5, 2 x power 1.5 and 3 x power 1.5, and I get another set of family of streamlines. This is what we have been emphasizing, that this represents a set of streamlines at that instant t equal to 0. These represent another set of streamlines at time t equal to 0.5. That is why we say streamlines are instantaneous. Now, if you draw tangent to that, of course, they are all straight lines, you will get the velocity over the entire region. And now if you draw tangent, of course these are curves, if you draw tangent along for all these curves at different locations, you will get the velocity vector in the entire region. Okay. So, very good example to illustrate that streamlines are instantaneous flow patterns and they change from time instant to time instant. Okay. This was not the attention of the earlier example. So, we took a steady state example. Okay. Okay. Path lines for unsteady flow. Okay. So, we start with the given velocity field V x equal to x by 1 plus t and V y equal to y. Now, path lines from t equal to 0 to given time t, which I have seen earlier. Okay. These steps are similar to the previous example. The velocity of the particle is equal to the rate of change of its x coordinate is equal to the x component of the velocity field, which is equal to x by 1 plus t. Similarly, in the y direction V p y dy by dt is equal to V y is equal to y. Now, this step is also we have seen earlier. I have a differential equation, no longer t is a constant, remember t varies along the path line. So, we cannot take it as a constant as we have done for streamline, and t is the independent variable. So, I have to integrate this equation dx by dt is equal to x by 1 plus t. I have to integrate this equation dy by dt is equal to y. We need initial conditions. So, at t equal to 0 the particle is at a point x naught y naught. So, we integrate these two equations, a rearrangement dx by x is equal to dt by 1 plus t, integrate ln x on the left hand side, ln 1 plus t on the right hand side, ln c1 as a constant. So, the equation for the x coordinate of the particle as a function of time is given by this expression x equal to c1 1 plus t. Okay. Now, we will have to evaluate the constant c1. What is that we know about the particle? We know that the particle x coordinate is x naught at t equal to 0. So, substitute t equal to 0 here, x will be equal to x naught. So, c1 becomes x naught. So, evaluate this constant. Please keep this in mind when we later on discuss streak lines, there will be a difference in the way in which we evaluate the constant, because the condition that we know is different, the condition what we know here is different. So, we know the initial condition t equal to 0 x equal to x naught. So, we get this expression for the x coordinate. Let us repeat this for the y direction, dy by y is equal to dt, integration gives ln y on the left hand side, t on the right hand side, the constant of integration is ln c2, which you can express as y equal to c2 e power t. Now, evaluate the constant of integration as we have done along the x direction. We know the y coordinate. So, substitute t equal to 0, y equal to y naught, c2 becomes y naught. So, the equation for the y coordinate of the particle as a function of time is given by this equation y equal to y naught e power t. So, these two equations together tells you how the x and y coordinates change as a function of time for the particular particle. Okay. Okay. At an instant find x and y position of particle, that is what I explained to you now. Now, you can find for a range of time t equal to 0 to given time the x and y positions. Now, as we have done in the earlier case, I can eliminate t, t varies along the path line. So, we can eliminate t, so that I can plot y versus x. Finally, the path line is a plot between y and x. So, we will have to eliminate t. Okay. So, how do we do that? This is the variation of x coordinate with time and this for the y coordinate with time. So, we will take this equation and express t in terms of x and x naught, and then substitute in the second equation for t, which means we have eliminated the time variable t. So, take this equation, rearrange and write it for t, substitute here, so that t gets eliminated, and this is the equation for the path line. These two are the equations to get the x and y coordinate as a function of time. If you are interested in getting only the final expression for the path line, eliminate t, and this will be the equation for the path line, which tells you how y varies as a function of x, which are the y and x coordinates of the particles. Remember, for given initial position x naught and y naught, okay. And that is what is shown here in this figure. I have taken different initial positions x naught and y naught, okay, and then drawn the path line. How do you plot these path lines? How do you calculate them? Let us take this particular path line. The x naught value is 0.01, y naught is 40. So, I know these values, I know x naught, I know y naught. Then it is a matter of taking different x values and calculating y values. I will just repeat, I know the value of x naught, I know the value of y naught, in this particular case 0.01 and then 40. Then what do? I vary x and then calculate y using this equation, okay. So, and such plots are shown here for initial position of 0.01, 40. In this particular case, if you see in this region, which means we are closer to the y axis, the given velocity field is given by x by 1 plus t and then V y equal to y, and because you are almost close to the y axis, the x component of velocity is very small, y component has a large value. That is why the particle starting here almost travels vertically, Over the time period, the distance travel along x direction is very less, but of course travels a long distance over the y axis, because the y component is much higher than the x component, okay. Now, similarly, if you take this other extreme where the particle lies on the x axis, okay, the y velocity is 0, okay, and you have only component, the x component of velocity, and that is why it just travels along a straight line. So, this almost travel along a vertical line, and this travels almost almost perfectly travels along the x axis. You can also see that from this equation also, when y naught is 0, y remains 0, and that is why this particle travels along the x axis, okay. Of course, intermediate locations have different path lines based on the x naught and y naught values, okay. You can also see that these path lines do not coincide with the streamlines which we have seen. It is a unsteady state flow field. We had streamlines change based on the instant, and these path lines do not coincide with the that of those of the streamlines, okay. Okay, streak lines, okay. Keep repeating this diagram, which is very illustrative, okay. As we go along, we will also keep this figure in mind, so that we understand better, okay. We are given the velocity field V x as x by 1 plus t, V y equal to y, that is the starting point. Remember, visualization of flow patterns, the given velocity field could be measured, could be simulation, we are representing using different visualization ways, okay. Okay. Just to recall, streak lines at an instant of time, they are at an instant of time for particles which have passed through a point x naught y naught over a time period. Because I need to introduce one more time, I used nomenclature t dash, what is the meaning of T dash? T dash tells you the time at which a particle enters or is at the point of interest or enters the domain. In this particular case, the point at which a particle is at this location is T dash for us, and that T dash varies from 0 to t. What is t? T is the present time. T dash varies. The example which we are going to take, t is 2. We are going to plot the streak line at t equal to 2. So, we will have to consider particles which have entered from 0 to 2, 0, 0.5, 1, 1.5, 2. So, streak lines at an instant of time for particles which have passed through a point x naught y naught over a period of time from t dash equal to 0 to t dash equal to t. Okay. The first two steps are same as that of the path line. What is that? Find integrating the equations. So, this is the rate of change of x coordinate of the particle is equal to the x component of velocity field, which is given by x by 1 plus t. Similarly, dy by dt is equal to Vy is equal to y. So, this is same as that we are seeing for the path line. Now, we integrate this step is also same as that for the path line. We will integrate this left hand side ln x, right hand side ln 1 plus t, constant ln C1, we get this equation x equal to C1 1 plus t. Okay. Let us do this for the y direction as well, and then we get the equation y equal to C2 e power t. Until this the steps are same. Now, how are we evaluating the constant? That is the difference between path line and streak line. In the case of path line, we know that what is known to us is at t equal to 0, that particle was at the position x naught y naught. What is known here, at some time t dash, a particle is at this position, some other next to t dash, some other particle is here. So, the condition known to us is at time t equal to t dash, we know the coordinate, not at time t equal to 0. We know the condition at which the particle is entering, the first particle let us say 0, then first second, etc. So, t dash, time at which a particle is at x naught y naught. I would define that to begin with itself. Okay. Time at which a particle is at x naught y naught. So, the conditions, the initial conditions which we know are at a time t dash, which is equal to or less than t, less than or equal to t. For the example, t we are going to take is 2 seconds. So, t dash we will take as 0, 0.5, 1, 1.5 up to 2. So, at time some t dash less than or equal to t, we know the position of the particle x equal to x naught, y equal to y naught. So, to evaluate the constants, I should substitute t equal to t dash here and then x equal to x naught here. In the earlier case, we just substitute t equal to 0 initial time and we evaluated the constant, but here the what we know about the what is that we want to know to evaluate the constant, we should know the position of the particle at some particular time. In the earlier case it was time t equal to 0, the present case it is at some time t equal to t dash. So, we use this equation, substitute t equal to t dash and of course x equal to x naught and evaluate the constant as C1 x naught by 1 plus t dash. Now, similarly we do for the y direction, y naught equal to C2 e power t dash. What is that I have done? I substituted t dash here and y is equal to y naught, rearrange and get the expression for C2. Okay. So, C1 is equal to x naught 1 plus t dash, okay, and C2 is equal to y naught e power t dash, and that is what is shown here. X is equal to C1 1 plus t, C1 was the constant of integration. We found out that C1 is equal to x naught by 1 plus t dash, substitute, you get this equation as x equal to x naught 1 plus t by 1 plus t dash. Similarly, in the y direction we had y equal to c 2 e power t. We found out the constant of integration as y naught by e power t dash, substitute here and then the equation becomes y equal to y naught e power t minus t dash. Now, what is the significance of these equations? Okay. To do that, let us go to this figure shown here. These are equations for the path line of particles, different particles which were at x naught y naught at t dash, and t is a time which varies along the path line. So, these are just path line equations, but for different fluid particles. Let us take the example here. Let us say our point of injection is 1 comma 1. So, x naught y naught is 1 comma 1. Now, I consider the fluid particle which was at this location at t dash equal to 0. Our current time is t equal to 2. So, how do I use this equation? I substitute t dash is equal to 0, vary t from 0 to 2 seconds and then get this curve which represents the path line of the particle which was at this location at the 0th second. Right now the particle is here and this is a path line which was followed by the fluid particle. Now, let us take the second particle which was at this location at t dash equal to 0.5 seconds. What do I do? Now, I take t dash is equal to 0.5, once again vary t, now from 0.5 to 2 I get this path line of the fluid particle which was at the location 1 comma 1 at the 0.5th second. Similarly, this is the path line of fluid particle which was at 1 comma 1 at the first second. This path line is not visible in this scale, and t dash equal to the particle is just entering. So, it is at 1 comma 1 itself, it is not even just into the domain. Okay. So, we have got several path lines for t dash equal to 0, 0.5, 1 and then 1.5 and then 2. So, these two represents the x and y coordinates of the different fluid particles. The difference comes because of the fact that t dash varies for different fluid particles. Okay. Now, so we draw path lines from t dash to the current time t, that is what we have done. Okay. X naught y naught is 1 in our case, the current time is 2 seconds. An example as I have illustrated, t dash equal to 0, we get x and y by varying t equal to 0 to 2. Now, how do you get the streak line which is of our interest? You can join all the end points of the path line. Please keep this figure in mind. The streak line is obtained by connecting the end points of all the path line, and exactly if you do the same procedure here and then connect by a smooth line, you get the streak line. Okay. Other way of doing that is, for the case of path line, t varied along the path line, but for a streak line what varies is t dash, the time at which different particles enter at our location 1 comma 1, that t dash varies from 0 to 2, and so in this case we eliminate t dash to get equation of streak line. How do you do that? Take this equation for the x coordinate as a function of time and rearrange that for t dash. In the case of path line we are rearranged for t, of course there was no t dash there, and then substitute in the expression for y. In this present case we rearrange for t dash because that is a variable to be eliminated, we get this expression for t dash and then substitute in this equation for y, so that we have an expression relating y and then the x, which are the y and x coordinates along the streak line. How do you use this equation? Remember, we are interested in plotting streak line at a particular time instant, and that is in this case t equal to 2, and what is x naught y naught, our point of injection 1 comma 1. So, I know constant value of 2 t equal to 2 and x naught y naught is known to me, and then now I vary x and then find out y, and then you straight away get the streak line equation, or you can straight away plot the streak line. So, if you want to, if you are interested in plotting the streak line alone using this method, you can use this equation and get y comma x, but if you are interested to show this kind of path lines also, then use the earlier approach as we have discussed, where we plot all the individual path lines and then connect the endpoints of the path lines to get the streak line. Okay. These streak lines are what we experimentally measure, as I have told earlier, by injecting a dye or injecting a smoke. Okay. If it is a gaseous medium, inject a smoke, let us say colored smoke. If it is a liquid medium, we inject a dye, and what we measure is this streak line. If it is steady state, then this streak line becomes same as path line and then streamline, otherwise it is not the same. Okay. But we should keep in mind what we measure is actually a streak line, because we continuously keep injecting particle and we take a photograph which is their position after some time from their point of injection, time of injection. Okay. As I told you, t of course the current time, a constant, which in this case is 2. So, just to summarize what we have discussed, streamlines are the tangent to the streamlines gives us the velocity, they are instantaneous, by this time should be clear. Path lines, path followed by a fluid particle, for a period of time, it is for a period of time, measured by taking video, okay, because it is over a period of time. Streak lines, locus of several fluid particles passing through the same point at a particular time. Okay. We talked about streak line at a particular time and measured by taking photograph. The keywords are video and photograph, you will never forget. Everybody likes camera, everybody likes video, everybody likes photograph. So, path lines video, streak lines photograph, we will summarize this.